Hi, this video is designed to give you a better understanding of the compensated demand functions that we developed in class. And so in this video, what I'm going to do is first work on making sure that you understand some of the intuition behind what we've done a little bit earlier in the semester, and then what the intuition is behind a compensated demand function. And then towards the end of the video, we'll actually go through and derive derive the compensated demand functions for two different utility functions. So first and foremost, we're going to review a bit of earlier material, and specifically what we're going to review is the idea behind what I've oftentimes referred to as just a demand function, or what I'll now call a regular demand function. There's another term that you'll hear economists use to describe this type of demand function, and that's a Marshallian demand function. And what you want to remember about this is a demand function, what I'm now calling a regular demand function, is ultimately solving the problem where a consumer is looking to maximize his or her utility, subject to staying on a budget constraint. So you'll notice that on this line, I've written that problem out in words. I'm maximizing my utility, ST, or subject to, making sure that my spending on goods X and Y is equal to my income. So PX times X plus PY times Y is equal to income. Now, when we were first learning about the idea of maximizing utility subject to staying on a budget constraint, we looked at a graph like the one that's on this whiteboard page. And if you recall, the idea behind what we ultimately looked at, we had a budget line or a budget constraint, which I've graphed in black here and labeled as budget line 1. And ultimately, what I was looking to do was stay on that black budget constraint, but I wanted to get to the highest possible indifference curve that I could reach. So in this picture, what we can see is that we would love to be at a bundle like Z. Z is on an indifference curve U2 that is higher than the indifference curve U1 or higher than the indifference curve U0. But I can't afford bundle Z. It's beyond my budget constraint. So even though I'd really like to be there, I can't be. So we turned our attention then to figuring out why, in fact, we would want to choose bundle B as opposed to choosing bundle A or bundle C. Now, again, the graph makes this pretty clear. The graph shows that bundle B is the highest possible indifference curve that we can reach. And if you recall, what's special about what's happening at bundle B is the budget line is tangent to the indifference curve at that point. And one of the things that we talked about was the fact that that meant that the bang for the buck was equal across goods. In other words, the marginal utility per dollar for good X was equal to the marginal utility per dollar for good Y. So again, remember that that bang for the buck condition, which I've got in the blue box, is just coming from what we see in the graph, namely that the marginal rate of substitution, MUX over MUY, is equal to the slope of the budget constraint, which is PX over PY. Now, again, just as a reminder, we talk about all of these things in absolute values, so you won't see the negative signs appearing. If you need to ultimately have a refresher on why we're choosing B and not bundle A or bundle C, you might want to refresh your memory by looking at the optimal choice video that is available from earlier in this series. But again, just to recap, the thing that I want to emphasize with this picture is that the goal behind what we're seeing here is that we want to stay on that black budget constraint, and we ultimately want to reach the highest possible indifference curve that we can, subject to staying on that budget constraint. Okay, so how is any of this different than what we're going to be doing in the rest of this? Looks very similar to what was happening in B or at bundle B in this picture with compensated demand. Well, compensated demand functions, which are sometimes known as Hicksian demand functions, Compensated demand functions are the solutions that we get from doing a different type of math problem. And ultimately, the intuition that we're after with compensated demand functions is going to be something like this. In this case, what we're looking to do is minimize our spending on good X and good Y. So minimize your spending on goods X and Y, subject to staying on a utility target. So we want our utility function to be equal to some utility level. I'll call that U bar. And so if we're thinking about how to approach this problem graphically, in this case, the goal that I have in mind is I want to make sure that I stay on a given indifference curve, a targeted level of utility, if you will. So I want to make sure that I stay on indifference curve U bar. But what I want to be doing is spending as little as possible in order to be on that targeted level of utility or on that target indifference curve. So what I'm going to do here is sketch in 3 different budget lines or budget constraints that I will label BL1, BL2, and BL3. These are all supposed to be parallel. And what that means is that for each of the 3 budget constraints, the slope of the budget constraint, px over py, is the same for all 3 of these budget lines. Again, the goal that we're after here is we want to spend as little as we possibly can while ultimately staying on our targeted level of utility or our target indifference curve. So you'll notice we have some choices that we can investigate here. Bundle A is a bundle that would put us on our targeted indifference curve, U bar. However, what you'll notice is that bundle A is on a budget line 3, that's farther away from the origin than either budget line 2 or budget line 1. And in particular, what we want to notice is that this budget line 3 is farther away from the origin than budget line 2. And this is of interest to us, particularly because while bundle A allows us to hit our targeted level of utility, we're not doing it as cheaply as we possibly can. And in fact, I'll label another bundle here, bundle C. Bundle C also allows us to achieve our targeted level of utility, U bar, but it's still going to ultimately cost us the amount of money associated with budget line 3. So keep in mind, each of these budget lines has an income or spending level associated with it. So budget line 1 has income level or spending level 1 associated with it. Budget line 2 has a different level of income or spending associated with it. And budget line 3 has yet another level of income or spending associated with it. And the key point here is that ultimately the level of spending or income associated with budget line 3 is greater than the income or spending level associated with budget line 2, which is greater than what's associated with budget line 1. And so what we can see here is that if we're trying to hit our utility target, our indifference curve U bar, choosing bundle B is going to ultimately be a better way for us to achieve this goal. And in particular, it's the best way possible that we can achieve this goal of hitting our utility target and doing that with as little spending as possible. Now you'll notice that what's happening at B in this picture, in both cases, our bang for the buck condition ends up being satisfied. And again, where this is coming from, as I had shown on the previous slide, it's coming from the fact that the slope of the indifference curve, or the marginal rate of substitution, is equal to the ratio of the prices. And you'll recall that the marginal rate of substitution is just MUX over MUY. So where that bang for the buck condition is ultimately coming from is simply the tangency at B, where the marginal rate of substitution is equal to the slope of the budget line. So again, this is the intuition behind the problem that we're trying to solve mathematically when we're deriving compensated demand functions. So as we move to the next slide, what that mathematical expression is giving you, it's giving you a recipe for the coordinates for a bundle like B. So if I knew the targeted level of utility, U bar, and if I knew the prices for good X, and that number would ultimately be the X coordinate for bundle B. Once you've found the compensated demand function for good Y, what that ultimately is doing for you, it's giving you the recipe that you need to find the Y coordinate for bundle B. All right, so we had gone through and done this derivation for the Cobb-Douglas utility function x times y in class. You've now seen this a second time, but just to make sure that, let's just look at the Lagrangians that we would set up for the Marshallian or regular demand. Here we're trying to maximize utility. Subject to staying on a budget constraint. And I obviously didn't write this down as a first step, but let's assume that we're working with the Cobb-Douglas utility function that we worked with extensively in class, namely u is equal to x times y. So if we're deriving the Marshallian or regular old demand functions, this is the Lagrangian that we set up. You'll recall we ultimately set up the first order conditions and we solve for equations 1 and 2, and then we ultimately get to the demand functions themselves. With our compensated or Hicksian demand, the math problem we're going to set up is going to be a bit different. We're still going to be putting our objective function first in the Lagrangian, but you'll recall that what we're trying to do this time is minimize spending on goods X and Y, subject to hitting a utility target. Now you'll notice for the constraint in the second Lagrangian, what I've basically done is I've taken the utility function and I've simply rearranged this so that X times Y is subtracting out the targeted level of utility, and I'm setting that equal to 0. Okay, so let's go ahead and work through this math problem. We've already done this in class, but I think it's worth seeing again. So we're going to set up our first order conditions. We're going to differentiate with respect to x, with respect to y, and with respect to the Lagrangian multiplier. So as I differentiate with respect to good x, I'll get p sub x minus lambda times y, and I set that equal to 0. Py minus lambda times the marginal utility of y, which is just, in this case, x. And our final first order condition is going to give us back our constraint. Remember that final first order condition is always going to give us what I call equation 2. So we're just getting our constraint back. X times y is equal to our targeted level of utility. For the first two first order conditions, you'll notice that what I can do is solve explicitly for lambda. So I'll have the price of good X divided by y. In other words, the price of X divided by the marginal utility of X. For the second first order condition, I can get the Lagrangian multiplier equal to the price of good Y divided by the marginal utility of Y, which in this case is just X. So I'll take those two expressions. I'll set the following equal to one another. And this is basically just my bang for the buck condition turned on its head. And this is my equation one. So to find compensated demand functions, what I need to do to finish this process off, I need to plug versions of equation one into equation two. So you'll notice if I solve this explicitly for y, I am going to get the following expression. If I rearrange this to solve explicitly for x, then I get that expression. So those are just two different mathematical versions of equation one. I'll take the expression where y is equal to px over py times x, and I'm going to plug that into equation two. So I'll have x times, now plug in for y, px over py times x equal to the targeted level of utility. And so I'll have x squared equal to targeted level of utility times py over px. And as the last step, I'm going to take the square root of both sides. And so I'll have the square root of u bar times py over px. So you'll remember from class that this is the expression that we found for the compensated demand for good X. I'll leave it to you to go back and plug the second version of equation one back into equation two to find the expression for the compensated demand for good Y. But what we do want to just make sure that we reinforce here and good Y respectively, I'd plug all of those pieces of information into my compensated demand function, the one in the blue box. That would spit out a number. We're all on the same page and that this is clicking for you. Let's take a look at the derivation for compensated demands for a different utility function. So I'm going to do a second example here, and what I'm going to do is now use the utility function. This is one of our quasi-linear utility functions, and I'm going to use the utility function x to the 1/2 plus y. And so what we'll do is, again, set up our Lagrangian. We're going to look to minimize our spending on x and y, subject to staying on our constraint. And so, again, what I'm going to do up here is, oops, I am going to rearrange this so that it's the utility function x to the 1/2 plus y minus the targeted level of utility equal to 0. So I'll just plop that down inside of my parentheses. And now I've got my Lagrangian. And I've managed to move the page on you. Well, this is what you get when you have old guys in technology. They manage to rearrange things and create a mess. Okay, well, hopefully you can see that well enough where it won't be a problem. let's set up our first order conditions. So we'll take the partial derivative of the Lagrangian expression with respect to x and y and the Lagrangian multiplier. So we'll take the partial derivative of the Lagrangian with respect to x. We get px minus lambda. And then we're going to set that equal to 0. We'll take the partial derivative of the Lagrangian with respect to y. We get py minus lambda times 1. Set that equal to 0. And as we're used to seeing, when we take the partial derivative with respect to the Lagrangian multiplier, we're going to get the constraint back. So I'll take that final first order condition and I'll just rearrange it so that we get our constraint back as equation 2. And now let's go back up to the first two first order conditions. So the first order condition, we will go ahead and rearrange this and we'll get lambda equal to the price of good x divided by 1/2 times x to the minus 1/2. And then the second first order condition is going to be extremely simple. Lambda is just going to be equal to the price of good y. Well, we've got these two things each equal to lambda, so they're equal to one another. We'll go ahead and set them equal to one another. And we'll go ahead and do a little bit of algebra on this. And keep working this out so that we have isolated the square root of x on the left-hand side. Oops. Well, it's very helpful to have isolated the square root of x on the left-hand side, but what we want to solve for is actually x. And so we're going to need to square both sides. So x is going to be equal to py squared over 4 times px squared. Now, this is what I typically label as equation 1. You'll notice that this equation in the box has come from my setting the pieces of the first order conditions equal to one another. In other words, this is coming out of that concept of making sure that the slope of the budget constraint is equal to the slope of the indifference curve, or that the bang for the buck across goods is equal. But you'll notice that there's something a bit unusual about this version of equation 1. This version of equation 1 does not have any y, doesn't have the variable y, in other words, on the right-hand side. So what we see on the right-hand side here are simply the prices of goods x and y and numbers. So it's a surprising result, but what we've actually derived here is the compensated demand for good x. The compensated demand for good x is popping out of this process earlier than it normally would. So we've actually already found the compensated demand for good x. But we still need to use this equation, plugging 1 into 2 in order to find the compensated demand for good y. So I'm going to take what's in the box next to the symbol for equation 1. I apologize. There's going to be a jump in the audio at this point. Murphy's Law, I got a telemarketing call in the middle of recording the video at this point, and so it shut off the sound, and won't bore you with the details, but in any event, I had to interrupt and back up, and hopefully we'll be able to make some progress from this point. So we were just about to plug equation 1 into equation 2, and so what I'm going to do is write the py squared over 4px squared And that's all going to be to the 1/2 power. I add y to that, and that's equal to our targeted level of utility. So again, I'm just taking equation 1 and plugging in for x. And now I'll go ahead and take the square root of everything in the parentheses, end up with py over 2px plus y equal to u bar. And now as my final step, I'll isolate y on the left-hand side, and I'll have this. And so what I've got in the box is my second compensated demand. This is my compensated demand for good y. And now we've got the compensated demand for both x and for good y for this quasi-linear utility function u equal to x to the 1/2 plus y. So I hope the two separate derivations of the compensated demands associated with a Cobb-Douglas and then a quasi-linear utility function have been helpful. And hopefully the beginning of the video has helped out a little bit in terms of reinforcing the intuition behind what we're ultimately looking to do when we're solving these math problems. Thanks.